Okay, good morning and welcome to the next lecture on functional programming. First, some announcements. So the first announcement is the first exercise sheet is available now, but I didn't print them, so you have to download them from the web page and solve them. So the first exercise sheet is on the website, and this exercise sheet is due on Monday. That is April the 23rd. And on Monday there will be exercise course instead of lecture, so we switched this around a little bit. So today we do lecture, but on Monday we do exercise course. To solve these exercise sheets, you should do this in groups of 2. So please solve the exercise sheets in groups of 2. So with 2 of you together, you should submit 1 exercise sheet. And in order to get your name into our database, please don't forget to register for the exercises. I think almost everyone did this by now, but in case you forgot it, do it now or later today. So register for the exercises on the website of this lecture. Website of the lecture. Okay, so this is about the exercises, and then several people asked us about registering for the exam. So first of all, the master students, when they register for the exam, they get a frightening remark shown to them by campus about a prerequisite you need, and the prerequisite that you need is that you did not yet take this exam before as a bachelor student. So don't get confused. Okay, so on the campus website, you will see something like prerequisites, and the prerequisite is not introduction to functional programming as a bachelor. And this means you cannot take this exam again if you took it before as a bachelor. So most likely this is not relevant for you, and you can just ignore it. So I can write it down again. If you took this exam already, you cannot take it again. I mean, sounds pretty clear. So if you took this exam as a bachelor, you cannot take it again as a master. You can't take it again as a master, and that's the only meaning of this frightening looking remark that you see on campus. You can't take it again as master. And this remark appears when registering for the exam as a master. So when masters register for the exam. And finally, there's this question, how do I register for the exam if I'm not a bachelor student taking the bachelor course and I'm not a master student taking the master course? And the answer is nobody knows, and therefore the solution is send us an email. So unless you are studying in the bachelor program and you want to take the bachelor exam, or you're studying in the master program and you want to take the master exam, if you fall into some other category, send us an email. So registering for exam, so bachelors for bachelor exam and masters for master exam. And masters for master exam. Via campus. And this also includes students of master mathematics who take the exam. They take the bachelor version, but I think this doesn't appear in campus for them. So they are masters taking a master exam. And everyone who does not fall into these two categories, send us an email and register by email. And if things change, we will notify you. So all others, register for exam via email to us. Okay, we will also put this again on the website so that you don't forget. Okay, so this are all the organizational announcements that I had to do. Any questions concerning this? No. Good. Okay, so what did we do in the last lecture? Well, we started introducing Haskell declarations, and we introduced several new concepts. And the last concept that we introduced was the concept of local declarations. And this looked like this. So we had the concept of, man sieht nichts. Is this difficult to see? Yes, it is difficult to see. No, but this is visible, I think. So what we introduced was the following. If you declare a new function symbol, so you say, I have a new function symbol, which is declared by several equations with a left-hand side and a right-hand side, then you can add this where clause, and behind this keyword where, we have a sequence of declarations. And in the sequence of declarations, you can introduce additional functions or additional patterns, but they are only visible in this right-hand side. And these square brackets mean that this where clause can be there, but it doesn't have to be there. So this is not mandatory. And we had an example for that. And the example was this function roots to compute the roots of a polynomial. How did you switch this off? Please, it's not, I cannot switch it on again, this slide. You can do that? Because I cannot. So we had this function roots, which takes 3 floats. So if you could switch it on again, that. Okay, now I can again. So it takes a floating point number and another floating point number and another floating point number. And it returns 2 solutions, so a pair of 2 floating point numbers. And how did this definition look like? Let's repeat it again, and then I will modify it afterwards. So these were 2 solutions, minus b minus d divided by e, and minus b plus d divided by e. And, well, what is d and e? D and E are defined by local declarations. So D is this complicated square root expression. It's square root of b squared, so b times b minus 4ac. And E is 2 times a. And the advantage is that in this way, this sub-expression D and the sub-expression E, they are only computed once, and they are needed twice. So instead of computing this square root expression here and here, we only compute it once, and that's, of course, good for efficiency. Now, this looks too imperative for the average Haskell programmer, because curly brackets and semicolon, that's something that Haskell programmers don't like. This looks like C or Java. So this can be avoided. And I mean, as I said, Haskell programmers are lazy. So they want to write as little as possible. And in particular, they want to write no brackets whenever possible. And so the idea is, well, why don't we omit these brackets and why don't we omit the semicolon? And indeed, this is possible in Haskell because, well, that's a particularity of Haskell, not of functional programming in general. Haskell is sensitive to the layout of the program text. So it makes a difference whether your line starts here, or whether your line starts here, or whether your line starts there. So this makes a difference in Haskell, and this follows certain rules. And these rules are called the offside rules. So the offside rule for the layout of programs. So this is really something special for Haskell. This is not the case in other functional programming languages, but it turns out to be quite handy. So after a while, I mean, when you learn how to write programs in any programming language, there are certain styles how you should indent your lines, that not every line should start at the same column. But in other languages, this is just good programming style. In Haskell, you are more or less forced to do it correctly. So offside rules for layout of programs. So what's the idea? So rule 1 says, if I have a sequence of declarations, then the column of the first symbol in the first declaration, this determines where all the declarations in this block have to start at. So the first symbol in a sequence decals of declaration determines the leftmost column of this declaration block. Determines the left border or the leftmost column of this declaration block. And now the question is, what happens if the next line starts at the same column, or if it starts right of this column, or if it starts left of this column? So rule 2 says, if you have a new line that starts directly below the first line, so at the same column, then this is a new declaration which belongs to the same declaration block. So a new line starting in the same column is a new declaration that belonging to the same block decals. So in other words, if this is my first line and my second line starts directly below the first line, not to the left, not to the right, then this is a declaration which belongs to this block, and this is another declaration which also belongs to the block. Now the next question is, what happens if the next line does not start here, but here? So what happens if line number 3 starts further to the right? Well, if the next line starts further to the right, then this is not a new declaration, but it just continues the declaration in the line above. I mean, if you have a very long declaration, then it will not fit into a single line, and then you can continue in the next line, but you have to use some indent. It has to start not here, but further to the right. So a new line starting further right just continues the declaration in the line above. Continues the declaration in the line above. So for example, if I have a very small editor, I can write something like roots ABC equals minus B minus D divided by E. And now I have no space anymore, so I continue. No, here. I continue in the next line, and I have minus b plus d divided by e. So now I put this into the next line, but this starts not here, but further to the right. You can also let it start here, or here, or here, or here, but not here and not here. Okay? And now the last question is, what happens if the next line starts further to the left? That also has a meaning. And now the meaning is that this declaration block has ended, and this is a new declaration that does not belong to this block anymore. So a new line starting further left means that the declaration block that you had before has ended, and this new line does not belong to this declaration block anymore. Means that the declaration block decals has ended, and the new line does not belong to this block anymore. Doesn't belong to this block. So in other words, if I follow these regulations, then I can do without these curly brackets and without these semicolons. So let's modify the definition of roots. I mean, this where here, this continues this declaration up here. So this where should be somewhere not here, but somewhere to the right. And now here we start a new declaration block. And this d equals the square root expression is the first declaration in this block. And this is the second declaration in the same block. So if I write them directly below each other, I can move this curly bracket and this semicolon away. I can erase this, and also this, and also this. And that's fine, because Haskell knows here we start a new declaration block, and this is a new declaration that belongs to the same block. And if in the next line I start again at this column, then Haskell knows that this local declaration block has ended, and that's a new declaration which does not belong to this where block. Yes? If I would move, well, if I move the e further to the right, I need the semicolon, and I need also the curly brackets, because curly brackets and semicolon belong to each other. I mean, this is the way. If you write it like this, Haskell inserts the semicolon and curly brackets automatically and treats it as if these curly brackets and semicolon were there. Yeah.
Just when you invent by tabulators instead of space.
Yeah, that depends on your editor. So, I mean, the question is, how does your Haskell file really look like? I mean, on your editor, it may look fancy, but in the real file, you may have something else. So that actually depends on your editor. So it may work or it may not work. Try it out. So ideally, it should work, but you never know. So, but then the nice thing is, write it with proper layout, and then Haskell knows what you expected and does it correctly. So typically, Haskell programmers would write it like this, and they would not use curly brackets, and they would not use semicolons, but this is pure syntax. So in the syntax diagrams, I will write the curly brackets and the semicolon, but you can omit it if you do the layout properly. OK, so this is an interesting feature of Haskell, but nothing specific to functional programming in itself. Now, the last item that I want to introduce to you before we end the section on declarations is the concept of infix declarations. So the last concept that I will introduce, and then you know everything about declarations that you need to know for the lecture, is operators and infix declarations. So what's the idea? Well, you've seen that if you define functions yourself, then you apply these functions to arguments by first writing the name of the function, and then you have the arguments. So if we define plus ourselves, it's a function from int to int to int. And, well, plus xy is defined to be x plus y. And here you see the difference. So this plus is a prefix function. If you want to apply this plus, you first write the name of the function and then the arguments. Whereas this symbol here is an infix function. If you want to apply it, you write it between the two arguments. So first the first argument, then the function, then the second argument. So these are two ways of denoting functions, both of which are common in mathematics. And Haskell has these both notations. And now the question is, can you turn a prefix function like this into an infix function? And can you turn an infix function like this into a prefix function? And can you define these prefix functions yourself? And the answer to all these three questions is yes. So these infix, so the syntax for prefix functions is they are strings of which start with ordinary letters. And depending on whether the first letter is lowercase or uppercase, it's a defined function or a constructor. So a prefix defined function is a string with starting with lowercase letter. So something like plus. And if you have a prefix constructor, a prefix data constructor, it's also a string, but it starts with an uppercase letter. So something like true or false. And now these infix functions, they look differently. For example, this is an infix function, and this is not a lowercase letter or an uppercase letter. It's a special symbol. I mean, it doesn't belong to the alphabet from A to Z, but it's the special symbol. And indeed, an infix defined function is a string of special symbols, so something like plus, of special symbols. And it can be an arbitrary string. The only condition is it may not start with colon. So not starting with colon. And an infix constructor an infix data constructor is also a string of special symbols, but it does start with colon. So a string of special symbols starting with colon. And indeed, we know one infix data constructor already, namely colon itself. So if you remember what colon does, you can write things like insert 1 into the list 2, 3. So this is, again, an infix function. It's a data constructor. It is used to construct lists and, well, to distinguish defined functions, which are defined by an algorithm, from data constructors, which are not evaluated further. If they are infix symbols, they either start with colon or they don't start with colon. Now, how can you turn a prefix function into an infix function and vice versa? That's also possible. So let's first turn infix to prefix. Turn infix to prefix symbols. This can be done by writing round brackets around the symbol. So, I mean, we have this plus. Plus was an infix symbol, but if we do round brackets around the plus, it becomes a prefix symbol. So now we can write something like, apply this prefix function to 2 and 3. And this is the same thing as 2 plus 3, and the result will be 5. Or insert 1 into the list 2, 3. So syntax, I mean, this looks differently, but for Haskell, this and this is exactly the same. One of these things is this is translated into this, and then Haskell can look at prefix symbols only. So if you like, you can turn any infix symbol into a prefix symbol, and the converse is also true. So you can turn prefix symbols into infix symbols by putting back quotes around it. So, I mean, this plus that I defined myself is a prefix symbol, but if I write back quotes around it, it becomes an infix symbol, and now I can write 2 plus 3, and indeed the result will be 5. So you can turn one notation into the other notation if you like, but you can also define infix symbols yourself. So maybe plus and times and colon is not enough for you. You want to have more infix symbols, then you can define new infix symbols. Yeah, infix symbols always have 2 arguments. I mean, otherwise infix is a bit strange. So, okay, the concept infix symbol only exists for functions that take 2 arguments. Otherwise, it doesn't really make sense.
Exactly 2?
Exactly 2. I mean, yeah, exactly 2. Okay, so if you want to define such an infix symbol yourself, then you can do this. So defining user-defined infix symbols. If you want to do that, there are 2 questions that you have to answer. Namely, you have to answer the question of association. So you have to decide about the association and about the binding priority. So these are 2 questions that you have to answer if you want to declare a new infix symbol. So what does this mean? Well, let's not define plus, but let's define something where association makes a difference. So let's start with association. That's the first thing we have to decide upon if we want to define a new infix symbol. So suppose I define division myself, and I say, well, divide is a function that takes 2 floating point numbers and divides them. So divide of x and y gives me x divided by y. And now suppose I want to use this as an infix symbol. So I want to write down something like this. 36 divided by 6. But now if I do infix, I can be nasty and apply this divide again and divide this by 2. Now, if I write down this Haskell expression, what happens? I mean, if your function here is associative, then it doesn't matter whether you first do this division and then you do this division or vice versa. But division is not associative. So if you do this division first, then you divide 36 by 6, which is 6. And then you divide by 2. And so this could be 3. But if you do this division first, you divide 6 by 2, which is 3. And then you divide 36 by 3, which is 12. So what's the result of this expression? Is it 3 or 12? Mm-hmm.
I think it means 3 because it's evaluated from the left.
Yes, indeed, it's 3. At least I hope. You can try it out. It is 3, but yeah, because you evaluate it from the left. But why not evaluate it from the right?
Because that's just how Haskell does it in order to evaluate.
Lazy evaluation makes sense if you have something nested. Then you can say, I do leftmost, innermost. But this isn't really nested. I mean, brackets are missing here. It's not. I agree that this is more to the left than this, but yeah. Okay, maybe for that reason, Haskell decides to do this first if you declare nothing else. But if you declare an infix operator yourself, you can say, should this associate to the left or should it associate to the right? For example, if you write 1:2: empty list, then actually this associates to the right and not to the left. So this stands for do this first and then do this. Otherwise, it would not be well typed. So there are some infix operators where you want association to the left and some infix operators where you want association to the right. And so if you declare a new infix operator, you can say what you want. So you can do an infix declaration. And the keyword for an infix declaration is infix, and then either an L or an R. So there's a keyword infix L. And if you say infix L divide, then we declare that divide is an infix operator that associates to the left. So this declaration means we associate to the left. And if we associate to the left, then Haskell would insert brackets automatically and do this first. And well, 6 divided by 2 is 3. So the result would be 3. And this is indeed the default in Haskell. So if you don't declare anything, then Haskell does that. So this is the default in Haskell. But you can also instead say infix R divide. And that means that divide associates to the right. So associate to the right. And in this case, the result would be 12. And indeed, the colon operator associates to the right. And there's a third possibility. You can also have the declaration infix without L or R. And that means it does not associate to the left and it does not associate to the right. So you may not write expressions like this. If you want to write something like this, you have to put brackets. So if you have this declaration and you write that, then Haskell will complain and the compiler will reject this kind of expression because it's ambiguous. So no association. And that means expressions like this are not legal. Expressions like the one above are illegal. So this is something that you have to think about if you want to use infix operators. How should this associate, or do you want to exclude these kinds of expressions that look like this? Yes?
Can we create infix symbols without using those tiny backslash?
Yes. Yes. I'll do it as soon as I wipe the board.
Where do you put the declaration?
The what?
Where do you have to put the declaration?
It's somewhere in the program. It's another form of declaration, so we will extend the forms of declarations. There will be another form, which I call infix declaration. And typically you do this before declaring the function. So first the infix declaration, then the type declaration, then the function declaration.
And if you do multiple times, like can you change it later on?
No. I mean, you should. For one infix operator, you do it once, and if you do it twice, I'm pretty sure the compiler rejects this. Now, this is not Prolog, where you modify your program during compilation. This is a function designed with the goal of clarity in mind. So this is something you shouldn't do. OK, so I said that association is one thing that you have to think about when declaring new infix operators. And the other thing that you have to think about is binding priority. Binding priority. And to illustrate this, let's look at an example. And this example also shows how to declare new operators having special names and not using these back quotes. So let's say I want to have a new infix operator that looks like this. I mean, infix operators, if you declare them yourself, then they are strings of special symbols. And depending on whether it's a constructor or not, they start with colon or they don't start with colon. So this is not a constructor. It doesn't start with colon. It should be a function from int to int to int. So the type declaration would look like this. I turn it into a prefix symbol here to declare its type. So it's int to int to int. And now I give defining equations. And, well, the defining equation for this is x person y is addition. So if I think that this is hard to read and this looks much clearer, then I give it a new name and call it person. But this means plus now. And let's also do it for times. So I introduce maybe a new symbol at. which is also from int to int to int. And x at y should be multiplication, so this should be x times y. So these are legal declarations. And now the question is, what happens if I write something like this? 1 %, 2 at 3. So what's the result of this? So this stands for plus and this stands for times. And that's not so clear because, if you think of this as plus and times, then you learned in school that times binds stronger than plus, but nobody told you whether at binds stronger than percent or vice versa. So we have to decide. And, well, depending on what you decide, the result will differ. And so, if this binds stronger, then it's 2 times 3, which is 6 plus 1, so the result is 7. But if this binds stronger, it's 1 plus 2, which is 3 times 3, and the result is 9. So the result really depends on what will bind stronger. And to determine this yourself, in these infix declarations, you can also declare the binding priority. So infix declarations may contain the binding priority. And the binding priority is a number between 0 and 9, where 9 is the highest binding priority and 0 is the lowest binding priority. May contain the so-called binding priority. Between 0 and 9, where the default binding priority is 9. So let's do it. So let's say I declare the following. I say that both person and at associate to the left. And let's say percent binds stronger than at. So this now plus binds stronger than times. Why not? So this has binding priority 9. Whereas at has only binding priority 8. This other thing. So if I do this declaration, then this means that this symbol binds stronger than this symbol, and then the result is, well, it's 1 plus 2 times 3, so the result is 9. Yeah?
Why is it restricted to 10 levels?
Don't ask me. You could have done it for 1,000 levels. But yeah, it is maybe because people think that nested expressions with more than 10 different infix symbols look ugly anyway, and that is the point where you should start writing brackets, because otherwise it's unreadable anyway. Yeah.
If 2 operators have the same
Yes, what happens if 2 operators have the same precedence? That's a valid question. If 2 operators have the same precedence, then it's executed from left to right. Have the same priority, then we do execution from left to right. Okay, further questions? I think.
If you will mesh up some operators with x double percent y and then plus, and the sign is plus, it will execute from the left to right because it says the same.
It depends. So what happens if you do this? Well, you have to look up the definition of plus. And I don't know what the binding priority for plus is. Most likely not 9, because times has higher binding priority than plus.
If you will not define the time binding priority for double percent.
If we don't define, well, then it takes the default binding priority, which is 9. So if you don't give it a binding priority, Haskell gives it a binding priority, namely 9. And also all the predefined operators, they also have a binding priority. And which one it is, you can look up in the definition of the standard functions. I don't know what the binding priority of plus is, but it must be smaller than 9. But I don't know, 6, 7, 8.
So if we overload this double percent with this min plus, then it will be like 1/3 9. So it will be the maximum.
If we don't declare anything, so if we drop this declaration, the binding priority of this will be 9. Yes, by default. Yes.
So you have to pay to change the execution direction of the operator already has.
Well, if you put brackets. By brackets, you can always change the execution, like in ordinary mathematics. Things in brackets are executed first.
But both operators are executed from right to left and also left to right.
Oh, you mean how does the if you have operators that associate to the right?
Yes, the operators are from left to right. And my question was, does this affect the execution priority state and the priority?
Yeah, so this L or R only has an effect if you have two occurrences of the same operator. And I mean, if it's the same operator, then it has the same binding priority naturally. And then the question is what happens in this case. And in this case, this L or R determines in which order the execution takes place. If the operators are different, then this L or R has no effect. Yeah. Do you need the brackets in the type declaration? I'm not sure. Maybe you can try it out. Maybe it works without also. I don't know. I'm skeptical that it works without, but who knows?
Combine the index decoration with the type decoration, like writing index L% and then double quotes.
No. These are two different declarations that you cannot combine. So let's extend the definition of our grammar over here. So these infix declarations should be possible now as well. And so we introduce a new form of declaration in addition to the ones that we had before. Now there's also this infix decl, which stands for infix declaration. And how does an infix declaration look like? Well, first you have one of these three keywords, infix, infix L, or infix R. Then you may write one of these binding priorities. If you write none, it takes 9. And then you say which operator has this binding priority and this association. And if you have several infix operators with the same binding priority and the same association, you can declare them all at once using commas. So if I would give them the same binding priority, I could write percent, comma, at, and do this in one single declaration. Okay, and what are infix operators? Well, they are either variables, so defined functions that are executed when evaluating the program, or they are data constructors, and syntactically you can see this because they either start with colon or they don't start with colon. So that's the syntax. Yes?
Can you use the function before its declaration?
Can you use the function before its declaration? Yes, of course, because if you have mutually recursive functions, you must be able to use a function before it is declared. So think of a function f and a function g. F calls g, g calls f. And of course, you can write something like this. And so, yes, it's possible to use a function before its declaration. But it has to be declared somewhere, otherwise the compiler will complain. OK, so this was the concept of declarations. And as I said, well, there are 4 basic ingredients of Haskell: declarations, expressions, patterns, and types. So we now manage the first concept, declarations. And now we get to the next concept, the concept of expressions. But I guess I need... Oh, I have another blackboard here. So let's start with expressions. So this is section 112. Now that we know what declarations are, let's define expressions. And, well, that's in some sense the most central concept of functional programming, because if you want to evaluate a program, what do? You have an expression, and you start evaluating this expression. So let's present the grammar for expressions in Haskell. And every expression every expression has a type and a value. And if you type in an expression into your Haskell interpreter, then the first thing that it does is it checks whether the expression is well typed. So whether in this expression you apply functions only to arguments of the correct types. So you cannot write something like true plus false. I mean, that's plus expects a number and not a Boolean value. So to evaluate an expression, first the compiler or the interpreter checks whether it is well typed. The compiler checks whether the expression is well typed. And if not, it stops and gives you an error message. And only if the expression is well typed, afterwards the compiler is going to evaluate it. Then the expression is indeed evaluated. So we don't have to think about how to evaluate non-well typed expressions, because non-well typed expressions are not evaluated. The compiler stops and complains immediately. Okay, so now let's look at the grammar for Haskell expressions, and let's do one by one. And for every kind of Haskell expression, we will say what is the type of this expression and look at some examples. So the easiest form of a Haskell expression, I don't know what that was, is a variable. So what are Haskell expressions? Okay, so the easiest case is a variable. And, well, these variables are expressions. You know how they look like syntactically. They are strings starting with lowercase symbols. Unless you use infix symbols, then they are strings of special symbols, not starting with colon. So something like x, that's a variable. But also things that you use to denote function symbols. So something like square is also a variable. So these things are variables, and, well, every variable has a type. And that's what you need these type declarations for. In these type declarations, you can determine what is the type of a variable. Now, the next form of expressions are data constructors. So they look like this. Data constructors. And, well, syntactically, they are strings starting with capital symbols, so something like true. Or they are, if they're infix symbols, then they can look like this. And there's one exception. This is also a data constructor, and this is a string of special symbols, although this is not an infix symbol. I mean, this is the symbol for the empty list, so this is an exception. It's not a string starting with a capital symbol, but still it's a data constructor. So in that sense, syntactically, this is an exception. It's not a string starting with a capital letter. It's not a capital letter string. But still, it's a data constructor. Now, how does evaluation of these constructors work? Well, they are not evaluated at all. So they remain unevaluated. They are simply kept as they are. And what is the next thing? Well, the next expressions that we have are expressions of predefined basic data types. And there are some basic data types in Haskell, namely data types for integers, for floating point numbers, and for characters. So this non-terminal integer, that stands for arbitrary integers. So things like 0, 1, -1, and so on. These are also expressions. And what is the type of these expressions? Well, the type of these expressions There's a special data type for integers called int. In reality, there are more data types for integers, but in the lecture, we only look at int. So int, similar to int in languages like Java, these are only integers of a limited range, so they can be represented with 32 bits. There's another data type called integer, where you can have arbitrary large or arbitrary small integers, but we will not focus on this distinction any further. So let's just use int or integer, whatever you like, for integer numbers. Now for float, floating point numbers are also expressions, and they look as you might expect. So something like this, minus 2.5. That's an expression, or you can also have expressions like this. So 3.4 times 10 to the 23. I mean, this looks, the syntax is the same as in other programming languages. So you have floating point numbers, and okay, one moment. And there are data types for floating point numbers. For example, the data type float. There's also a data type double, and this is as in other languages. Yes?
In Java or I need to have float and postxf at the end, so that it's an actual float and not double. Is this true here?
This is not true here. So if you really, we will get to this later on, I guess, in the next lecture. What really the type of these things are. So why is this a float or is this a double? Or is this an int or is this also a float? And to understand this, one needs to know a bit more about the type concept of Haskell, because these types are in some sense related. So if you think of something like Java, you have subclasses and superclasses, and some object can belong to several classes, I mean to a class, but also to its subclass. And something similar happens here as well. So at the moment, let's assume they have type int, let's assume they have type float, let's not think about double, and let's postpone this until next lecture when we speak about the type concepts, about the concept of type classes in particular in Haskell, and then we can say a bit more about this. So in particular, I should maybe say, here I said what happens if you evaluate an expression. If you only want to know the type of an expression, that's most likely also possible with your favorite compiler. So for example, in GHC, if you say :t and then your expression will not be evaluated, but it just checks the type of this expression. And so if you try this out for lists or so, you will get the expected result. If you try this out for integers, then well, the type of this will not be int, but something more complicated. And to understand this output, you have to wait until the next lecture. Then I'll tell you what the output, what the real type of 0 or 1 or -1 is. At the moment, let's assume the type is int. By the way, this also helps you to solve the exercises on the exercise sheet, but that's not the purpose. So this, I mean, sometimes we have exercises like, give the type of this expression. And then what you should do is not type this into your Haskell implementation, but you should think about it yourself, because you should understand it. And one day in the exam, you have to solve this without a computer as well, but you can use this to check whether your result is true. So, I mean, you will find this out anyway, so I can just as well tell you. Okay, characters. Characters exist in Haskell as well, like in any other language. And characters, for example, to make sure that a is not a variable, but now I mean the character small a, you have to put it into apostrophes. So this, or for example, the character 0. This is not the number 0, but the character 0. Well, to distinguish it from the number, we use these apostrophes. And of course, there are also control characters. For example, this is the symbol for new line. And there are symbols for tabulator and so on. So this is pretty much like in other languages. And there's a special type for this, and the type is called character. So like in other languages, but with capital C. So this, in some sense, are the basic expressions, variables, constructors, and these elements of predefined primitive data types like integers, floating point numbers, and characters. And now, from these basic expressions, you can construct more complicated expressions. And one way to do this is to take several expressions, write a comma between them, and square brackets around them. So something like this. So if x1 and x2 and xn are expressions, then this thing is also an expression. And what is the meaning of this? Well, this stands for the list of n elements. This is the first element, and this is the last element. So this is the list of these n expressions. And this is only allowed, this is only well-typed if x1, x2, and xn all have the same type. So they must have the same type, so some type A, and then the list. So then this expression has the type list of A. So if these are all integers, then this expression has the type list of integers. And in fact, this is an abbreviation. This is just syntactic sugar. So something like this is, in fact, an abbreviation for the expression 0 inserted into 1, inserted into 2, inserted into the empty list. So this is easier to read, but Haskell converts this into this term. And you can see now that this expression is built by applying colon to 2 and empty list, and then colon to 1 and the result of this, and colon to 0 and the result of this, because colon associates to the right. Okay, so this is one possibility to construct new expressions. And these lists are a pretty central concept of functional programming. In particular, this also allows you to do text processing in a very easy way. So the next form of expressions are strings to do text processing. And what are strings in Haskell? Well, strings in Haskell are just lists of characters. So they are really lists like this. So for example, this is the list where the first element is the character H, then the character E, then the character L, then the character L, then the character O. And since this is ugly to write and to read, as long as it's a list of characters, Haskell knows a short way of writing it. So instead of this, you can also write these characters after each other, but with double apostrophes around it. So this is the string hello. And for Haskell, this is the same as this. So you can write this short notation, but Haskell converts it into this list. So there's a data type string for this. And so there's a type string. And in fact, this type string is identical to the data type list of characters. So this is rather convenient because you can now operate with strings as you would operate with lists. So you can write, for example, if you remember our length function, so this length function which does something for the empty list and something for the non-empty list. And this function, if you let this function work on lists of arbitrary elements, then it can also work on strings. So for example, you can now call len of hello, because hello is just this list. And so len also works on lists of characters, and it gives you the length of this list, and the length of this list is 5. So it's very easy to manipulate strings and analyze strings because it's just lists of characters, nothing else. And the only difference is that you have this short notation. Instead of writing this, you can also write this. OK, what is the next form of expression? Well, we've seen that you can put expressions, you can compose expressions by writing commas between them and square brackets around them, and then you have a list. Instead, you can also use round brackets, and then you have a tuple. So that's the next concept. So if you take n expressions, you write commas between them and round brackets around them, then we get the tuple of these n expressions. So exp1, exp n. and this is the tuple of expressions. And here the expressions do not need to have the same type. So if this has, let's say, the type A1, and this has type A2, and this has type AN, then what is the type of this tuple here? Then this has the type, well, it's a tuple where the first element is from A1, the second element is from A2, and the last element is from AN. So this is the notation of Cartesian product in Haskell. So for example, I can write something like the tuple of 10 and true. So 10 is an expression, true is an expression, and therefore this tuple here is also an expression, and this has the type int, bool. So because the type is, it's a tuple with two components. First component has type int, second component has type bool. And in Haskell, as you can see, you can also do tuples with only one component. So you can write something like this. But for Haskell, this is the same as the thing without the round brackets. So if you evaluate this, then for Haskell, this is the same as just 10. So this means whenever you have a single expression, you can write round brackets around the expression, and that changes nothing. That's very convenient because, I mean, if you have complicated expressions, you want to use brackets. And if you do that, well, this indicates in which order things have to be evaluated, but it does not change the value any further. And so if you want to write round brackets around something, you can do it, but it doesn't change its value. And tuples with no components, as you can see, n in this grammar, the number of expressions in there. So this n can also be 0, and this means the empty tuple is also allowed. And indeed, the empty tuple, that's a legal expression. And what's the type of this? Well, we've seen how to build the types. The type is also a tuple type, where the first component is the type of the first component of the tuple, and the second is the type of the second component. Well, this has no components, so the type of this is this. So this is a special type, the empty tuple type, and this empty tuple type has only a single element, namely this. So that's an awkward type with, it's a singleton type with just a single element. Sometimes people use this. If you don't like it, don't use it, but it's there. It does exist. So this is a special type with only one single element, namely this. With only one element, namely the element empty tuple. So this indeed exists in Haskell. Okay. Now there's another, yes? No, you cannot I mean, lists. The thing is, if you concatenate two lists, so something like this and this list, these lists you can concatenate. And indeed, there's a concatenation operator already predefined in Haskell, which is called plus plus. So this is a predefined operator to concatenate lists. And that's fine, because the result of this thing is the list 1, 2, 3, 4, 5. And they all have the same type. This has the type list of integers. This has the type list of integers. And this also has the type list of integers. But if you want to concatenate two tuples, so maybe the tuple 1, 2 and the tuple 3, 4, 5, they have different types. This has the type tuple of 2 components where both elements are integers. This has the type tuple of 3 components where they are all integers. And well, this, if you write round brackets there, this has 5 components. So there's no predefined operation which would turn these two things into a result like this. Of course, you can write a function which takes a tuple with 2 components and a tuple with 3 components, and gives you a tuple of 5 components. But for every component number, you would have to write new functions yourself.
So there's no easy way to change a predefined tuple?
No, there's no easy way to change a predefined tuple, because you have to think about, we have no side effects. Changing is not possible anyway. I mean, an object is never changed. An object remains like it is. You can have new objects, new results, but existing objects, they are not modified. That's very much against the spirit of functional programming.
So there's no way to insert a new element into a number?
No, not a direct way. You can define a function that takes 2 tuples, gets a new tuple, but modifying this, no. Yeah?
What is the type of a bracket in a bracket?
What is the type of a bracket in a bracket? You mean this?
Yeah.
Okay, what do you think?
Well, this should be the single type we defined earlier.
Right, so if you have round brackets around only a single element, it makes no difference. So this is the same as this, and the type of this thing is this.
I wondered if we could map this to the natural numbers, but we obviously can't.
No, not this. This has really just a single element. If you want to mimic the natural numbers, you have to do it differently, and we will see how.
But you can have a tuple with 2 empty tuples.
Yes, sure. You can have a tuple with 2 empty tuples. And that's okay, and the type of this thing is this. I mean, these are awkward things. I mean, they don't do this in programming, but yeah, if you want. Okay. Let's continue with the definition of expressions, but I have to wipe a board first. Okay, so the next way to create a new expression from existing ones is, it looks almost the same as the one above, but the commas are missing. So if you look at this very closely, you see that there are no commas, and this makes a difference. What does that mean? Well, we have seen this before. So now we have x1 to xn, but without the commas. And moreover, n is greater or equal to 2. So this only makes sense if you have at least 2 expressions. And this is function application. So for example, we have something like this, plus 2, 3. This is an expression, this is an expression, this is an expression, and they are just written beside each other. And, well, if these brackets are not needed, we can also omit them. And what does that mean? That means that expression 1 is applied to expression 2, and the result of this is applied to expression 3. And if you have more of them, then the result of this is applied to expression 4. So this is function application. So x1 is applied to x2, and the result is applied to x3, and so on. And of course, this is only legal if the types are correct. So x1 must be a function that expects an argument of the type of x2. So here plus expects an integer argument. And the result of this should be a function that expects an argument of this type. So again, it expects an integer argument. So the types have to match, otherwise this will not be well typed.
So if we add another number of the like plus 2, 3, 4?
Yes, if we add another number plus 2, 3, 4, we get a type error. So because this thing has type int, and now this thing has also type int. Now we apply a number, 5 in this example, to 4, and 5 cannot be applied to 4. So this is a type error. Yes?
Can we leave out the brackets?
We can leave out the brackets. Yes, you can leave out the brackets as long as there's no ambiguity. Yes, otherwise you can leave out brackets. So let's remove this 4 because this is really not well typed. Now this is well typed. Okay, so the next expression is something to relax because that's something you know from other programming languages as well, and it also exists in functional programming. Namely, there's an if-then-else, and this if-then-else expression does what you might expect. So if x1, x2, and x3 are expressions, you can do this. You can write if then else between them. So if x1, then x2, else x3. And, well, to make this legal, this has to be of the type Boolean. And these two have to have the same type. So it can be arbitrary type, but the same type. And what is the meaning? If you want to evaluate this expression, this if-then-else expression, first the condition is evaluated. And depending on whether the result is true or false, afterwards either x2 or x3 are evaluated. So it's the normal meaning of if-then-else. So let's give an example. You might recall that in the last lecture, we had this maxi function. And this maxi function worked like this. It took a tuple of two numbers, and it checked whether x is greater or equal than y. And if so, the result is x. And otherwise, the result is y. So you can write it like this. But if you don't like this notation with the guards, you could now also use if then else. So instead, we can also write the following. We can write maxi xy equals if, well, this is what we want to check. We want to check whether x is greater or equal than y. So if x greater equal y, if x greater equal y, then x else y. OK, so this is not very complicated. This is as in imperative programming. The next concept, so two more kinds of expressions are coming. The next one is also just different syntax for something that we know already. So we know that we can have local declarations. And up to now, the idea was we first write the expression, and then comes the keyword where, and then comes the local declaration. You can also turn this around. Instead of giving first the expression and then the declarations, you can also first give the declarations and then the expression. But then the keyword is not where, but let. So how does it work? So let, then we have a sequence of local declarations. Then we have the keyword in, and then we have this expression. And the meaning is that these are local declarations which are only visible in this expression here. And outside this expression, they are not visible. So this is very much like where. So let's define our roots function again, but this time we use let instead of where. So how did this work? So this roots function, a, b, c, we wanted to find out the roots of a times x squared plus b times x plus c. And the idea was that in the end we have this expression minus b minus d divided by e and minus b plus d divided by e. And the question is, what is d and e? D is the square root expression, and e is this 2 times a. And instead of writing where d equals dot 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 and where e equals dot dot dot, I can also do it in front. And then I use let. And of course, this layout rules, these offside rules that tell me how to indent the different rows, this also works with let. So let d be the square root of b squared minus 4ac. And e is 2 times a in. So it's important that these two are directly below each other, and that this in is further to the right, further to the left, to make sure that this declaration block ends here. And so this is again on top level. In has to be left of the d, yes. But not here. So it has to be right of the r, but left of the d. OK. So for example, here, or here, or here. So this is just a different notation. Depends on whether you want to put the declarations behind the expression or in front of the expression. So this is, again, for local declarations. And the last form.
The let thing is basically
Yes, exactly. So for example, in your interpreter, you can write something like, let x be 2 and y be 3 in x plus y. And this thing evaluates to 5. Because it evaluates to the thing after the in. So the value of this thing is the expression. But in this expression, you can use certain declarations, namely those declarations that are behind the let. So this evaluates to 5. So indeed, the value is exp, but it uses the local declaration. The local declarations in Deckel. Okay. Yeah.
Maybe there are some operators overloading in let definition, just like we did in the.
I think yes. I think you can declare everything except for new types. So, how to declare new types we didn't have yet. So anything that we had up to now, you can declare in here, including infix operators, also type declarations, of course. So things like this, they can all be in this local declaration.
What if you declare the function somewhere else in the program, and now you write the infix operator into that part?
That's fine.
So the infix declaration, sorry, so you change it in
So in here, you first look into the local declarations, and they override things that were declared further outside. So if you had another definition here where x was 7, but here x is 2, then here x is 2 and not 7. So this, local declarations, you first look into the local declarations, and if it's not defined there, you look into the topmost declarations. I think overwriting plus is not allowed, because plus is a predefined keyword function that you cannot override. But I think user-defined things you might be allowed to override.
But you can change the associativity of the function locally.
I think so, but not of the. I don't think you can do this for the predefined functions, but who knows? Maybe you can, but you shouldn't. So I think you probably can. I think some of these overloadings are possible, but they lead to completely incomprehensible programs. So I don't know, because I never did that, and I never want to do that. So you probably shouldn't do everything that is possible. I mean, try to write readable programs and avoid overloading things where everyone expects a certain semantics with the thing. So plus should compute plus and nothing else. Okay, further forms of expressions. Yeah, actually, I think you can do that. So one of my assistants once wrote a program. I think you could write 1, 2, 3, and 1, 2, and 3 were overloaded, and they meant something else. And so don't do it. Okay, so what's the next expression? So the next expression is syntactically different to what we've seen before, but it introduces nothing really new. It's the case expression. And this just is an expression which does pattern matching. So typically, you would do this with many different function declarations. Now you can do it in a single expression. So what's the meaning of this? So keyword case, and then you have an expression, and then you have the keyword of, and then you have many of these pattern expressions. And of course, you don't need to write it like this. I mean, these curly brackets and semicolons, I said already, Haskell programmers don't like curly brackets and semicolons. So typically, you would write it probably more like, you would probably write it like this. Case of, and now you have pattern 1, and then arrow exp1. And then pattern 2, arrow exp2. So this is how you would lay out this normally, and then you can avoid these brackets and these semicolons. And what does this mean? This means that we do pattern matching. So we check whether this expression is matched by this pattern. So does pattern 1 match expression 1? If yes, then the result of this whole expression is exp1. If no, we check whether pattern 2 matches this expression. If yes, the result of this thing is exp2, and so on. So check if pattern 1 matches exp, and if so, then the result is exp1. And otherwise, we do the same thing with pattern 2. So otherwise, check if pattern 2 matches exp, then the result is exp2, and so on. And there is no need to have a complete analysis, so it can be that none of these things matches. Then you get an error when evaluating this thing. So let's look at an example. Up to now, we defined Boolean conjunction ourselves using, for example, the German word und, which means and. So we had this form of pattern matching. Und true and y gives me y, and und false and y gives me false. And instead of writing this, I could use case, and then it looks like this. So und xy is now the following thing. I want to do a case analysis depending on the value of x. So this exp here would be x. Depending on the value of x, I do this or this. So I do a case analysis on x. And if x is true, then the result is y. And if x is false, then the result is false. So what case does is it does the same pattern matching that we had before, but instead of doing it in 2 equations or in many equations, I can do it in a single expression. I can do it in a single expression and therefore in a single equation. So not really a new concept, yes.
What about the types of the pattern? Do they have to be in some way, or can you, for example, write 2 as a list or something?
No. So this has to be type correct. So essentially the types of all these patterns and of this expression have to be the same. Well, it will be more complicated when we have type variables, but currently they have to be the same. So this is of type bool, this is of type bool, and this is of type bool. Yes?
What happens if no pattern matches?
If no pattern matches, the same thing as here, you get an error because it cannot evaluate any further. Yes?
Can we use something like the Java, like a default function that will...
Oh, you would like to have a default function here saying, well, if none of these things works, then that, no. But that would be convenient. Yes, of course, you can write Z and then something. That, of course, you can do, yes. And in fact, there's even a joker pattern, which is the underscore, which comes in the next section. So, okay, so yes, in that sense, you're right. There is a default pattern. This matches everything, or the Z matches everything. And so this will catch all the things that you didn't catch before. Yes, right. Okay. Okay, so these are all but one of the expressions in Haskell. And the last expression, that's something new that you don't have in imperative languages, the lambda expressions. And we will do that and the patterns and types in Haskell on Friday. So see you on Friday.